$100,000 a year.
While I'm honored to have known Alvy for a while. Is truly a pioneer of computer graphics. Let's see if you can summarize your career in 1 minute. First of all, PhD at Stanford University in computer science, I guess. Then his life moved to New York. He was at New York University. Then you came back to work at Xerox PARC, a legendary Xerox PARC when it was deservedly legendary. Then you went back to New York University, where Alexander Shure, do I mispronounce his last name?
Sure.
Sure. He started the computer graphics lab. You met Ed Catmull there, and I think Lucasfilm incubated what then became Pixar in 1980 something, 1985, 86?
86.
86. So Alvy is one of the two founders of Pixar, and so he's the one of the people who brought us computer graphics for entertainment, not just as diagrams and educational material. Okay, I met you several times while you were working on the book. I almost lost hope that the book would be finished. I have to say, Alvy gave a talk, exactly the same title, I think, 5 or 6 years ago, the big event that I organized in San Jose. So this is also personal. Finally, I see you talking about the book, and the book is actually
done. It's done. Yes.
Okay, all yours. I go away, and the podium is yours.
Here we go. Okay, so yes, I've been working on this book for 10 years based on the observation that we're surrounded now by pictures made of pixels. You know, I carry several billion pixels on my cell phone, and I suspect you do too. But the surprise is that so many people don't know what they are, even though nearly all pictures in the world are now made of pixels. And if people tell you what they are, they usually have the story wrong. I asked Google what pixels look like, and this is what it showed me last week. And I think this is what many people think pixels look like. They're little abutting squares of color. But in my talk today, I want to prove to you that this is not true and never has been true. Okay, and we'll talk about why that misperception is so common. Okay, I'm going to start right at the beginning. The theory that gave us the pixel starts with this man, Joseph Fourier, in about 1800, let's say. He told us, he came up with a theorem that basically said the world is all music. To be a little more specific, he said all music is a sum of sound waves that have this shape. So you can see that you add together Fourier waves of different frequencies, how fast they wiggle and how high they crest, to get any piece of music. I don't think anybody's too surprised by that. But he went further than that and said all sound is a sum, no matter how irregular the sound is a sum of these very regular Fourier waves. It's a kind of surprising result, but it's fundamental to all modern science and technology. He went further. He said, if you extrude those one-dimensional waves out of the plane and then look down on them, you see corrugations that look like this. And from those, you can add these waves, these two-dimensional Fourier waves, together to get any picture. And that's the basis of the modern media world. But there was one more step that had to take place before the pixel, and here it is. In 1933, this fellow, whom you probably have not heard of, nearly most people haven't, at least not in America, came along. Vladimir Ketelnikov is his name. He was a Russian. He came from a long line of first-class Russian mathematicians, 7 generations of them, all the way back to Euler. I think it was his great-great-great-grandfather was one of the 6 students of Euler, who was one of the greatest mathematicians of all times. So this guy was no slouch. And in 1933, he published a proof of the sampling theorem, which is what defines a pixel. We're going to spend a little time on this theorem because it's unbelievable. You'll see when I start describing it. You can't believe it's true, but it is the foundation of all modern media. Now, I don't read Russian, but I can read the mathematics in this paper, and it's exactly the math I use today for sampling. Now, I did spend a whole chapter in the book on this guy because he's such a fascinating character. But let me just show you one example of this person. This is the last photograph I found of him. Standing in the Kremlin with Vladimir Putin, adorned with all the merit badges of the Soviet Union, several orders of Lenin and several orders of Stalin and so forth. And Putin is knighting Ketelnikov, or whatever the equivalent to knighthood is in Russia, for proving that the sampling theorem, in other words, on the 70th anniversary of that paper at the top, he was getting this award in the Kremlin. So they know who he is in Russia. All I'm going to ask you to remember, oh, and one other thing about him before I move on is he came to America in 1957 and told us that Russia was going to put up a satellite. He told us about Sputnik 2 months before it went up. All I'm going to ask you to remember from this picture is that shape there, which I call a spreader, and you'll see why in a couple of moments. By the way, in America, we were all taught that the sampling theorem was proved by Claude Shannon, an American, of course, instead of this Russian communist. It was the Cold War times, after all. How could we give credit to a Russian communist? But Claude Shannon never even claimed he did it. Okay, so what is this theorem that so many people claim to have proved? Let's start with a one-dimensional example, and then I'll go to a two-dimensional example, and then we'll get back to that original picture of the little squares. This is a picture of a sound, the amplitude of sound versus time. So time is to the right. The straight line is zero loudness. This is changing amplitude of sound versus time. It's a sound signal. So the sampling theorem that Ketelnikov proved said the following thing. If you place dots, regularly spaced dots along that signal, that sound signal, and I'll tell you how you space those dots in a moment, but if you do it the right way, according to his theorem, you can throw away the rest of the signal and preserve only the value of the signal at the dots. We call those values at the dots samples. So what he said was you can throw away, if you do the sampling at the right rate, you can throw away the infinity of points in the original signal, an infinity of points between each pair of dots, and just carry the samples and not lose anything. He didn't say it's an approximation. He says it's a perfect representation of the original signal. It sounds like something from nothing. And I'll try to explain where those missing infinities come from or went to. So what's the spacing that's required by the sampling theorem? Well, remember, Fourier told us that any signal like that is a sum of one-dimensional Fourier waves. So Ketelnikov, in his theorem, said, find the Fourier wave of the highest frequency in the sum that is equal to the given signal and sample at twice that rate, twice that frequency. That's the magic. That's the magical sampling theorem. It's astonishing. That's the first half. The second half is, okay, so about 10 years later on the other side of the planet, you have your samples and you want to hear the sound that those samples represent. How do you get how do you get the sound back? Well, remember this shape? It's called a spreader. And what Ketelnikov taught us was what you do is you spread the samples with a spreader and add up the results. And that gives you the original signal back. Now, let me step through that. First of all, I need to point out that this spreader ripples off to infinity forever to the right and to the left. Therefore, it's infinitely wide, and we can't use infinitely wide things in the real world. It just doesn't work. So what we do is we substitute a very good approximation for the spreader. This happens to be a pretty good one. You see it's got the same middle peak and two negative pulses, negative lobes, but then it goes to 0. So it's finite width. We can use things of finite width in the real world. All right. Ketelnikov says, okay, spread each sample. And you can think of what that means is you put a copy of the spreader at each sample and adjust its height. So its height. The height of the spreader matches the height of the sample. And then you add it up. And you get that bold curve, which is magically the original sound signal back again. That's the sampling theorem. It's a marvelous theorem. Now let's jump to 2 dimensions, where the signal is a picture. You can think of it as the intensity versus space. And what we call the samples in that case is a pixel. A sample of a picture is called a pixel. That's the definition. And this is what the spreader looks like for the 2-dimensional case. If I drop a guillotine right down through the top of that hillock, you'll see that the cross-section is the same shape that we use as a 1-dimensional spreader. And here's a picture of one single pixel being spread by the spreader. Now let me stop here and say some fairly important things. A sample exists only at a point. A point is 0-dimensional. Therefore, you cannot see a pixel. Most people find that surprising. You cannot see a pixel. I said I had billions of pixels in here. I can't see them. You can't see them, right? You can only see them when you spread them with a spreader on the display. What are the spreaders on your cell phone? Well, those little glowy spots on the display, those are the spreaders. Now, some people call those little glowy spots pixels, but that's a category error. Pixels are discrete, separate, invisible things. The soft glowy spots are soft and glowy. You can see them and they overlap to form, by the sampling theorem, the original picture that the pixels represent. Let me point out a second thing. I've not invoked the notion of a little square even once, and I'm not going to. There are no little squares in the sampling theorem. So where did that notion that pixels are little squares come from? And I maintain that the culprit is the function that we call magnify or zoom that almost every app has. You know, people, I've had people say, "But I've seen pixels. I just magnify my screen, and there they are, and they're little squares." But I'm here to tell you that that magnify or zoom feature is a lie. It's a quick and dirty trick that made a lot of sense back in the early days of slow computers, but it does not magnify the pixels. I've made a picture here with Photoshop of 14 gray pixels. And of course you can't see it because they're tiny. So let's magnify by say 100 just to make this discussion easy. And you get something that looks like this. So one would conclude, wouldn't they, that the little picture must have been made of little squares. Pixels must be little squares, but it's not so. What magnify does, and it's really easy, but it's wrong. It replaces each pixel in the original image with a 100 by 100 square array of copies of that pixel. So of course, when it displays a 100 by 100 square array, it's going to look like a square, but it's not a picture of the original picture up close. If you magnify this picture correctly using the sampling theorem, it looks like this. You can think of each of these blobs here as being that little hillock I showed you earlier. You're looking down onto it. And they're not squares, they overlap and so forth. So I want to close by showing you the first pixels because I found them for the book I wrote. Much to my surprise, the first pixels were on the first computer. The first computer was called Baby, believe it or not. And it was built in 1948 in Manchester, England. And this is Baby's display. I went to see Baby in 2013 for part of my research, and on the screen, on its display, was this, and the word Pixar was scrolling to the right. So two things to notice. One is there are no little squares, even on the very first pixels. And there were pixels, and the first computer had pixels and it could animate. Now, nobody at the time actually did animate because there was the people who built this machine thought that was frivolous use of their fancy machine. But I poked a little further and I found the original image, the first image that was made on Baby, and this is it. Again, so an engineer did stop. The engineer who made this picture did stop in 1947. Actually, Baby was still under construction, to take this photograph. Again, these are the first pixels. This is the first digital image. I call it first light, and there were no little squares then. That's the end of my talk.
Thank you, Alvin. Yeah, so Alvin is very good at finding this trivia, even about the biographies of some of these people who were very interesting people. So now that you finished the book, what is the main thing you discovered writing this book that you didn't know before?
Oh, lots of things. The book is 550 pages plus long, and there are a host of things I uncovered. Several general ideas that came to light were that almost invariably, when I looked into the history of the high technologies, the received versions were bogus. They were just full of errors. They celebrated the wrong heroes, the wrong countries, the wrong machines. They were just wrong. And I think the reason is that we humans are just suckers for the simple narrative. We want a single hero from whom everything descends in a beautiful story. And it just doesn't work that way. It's a very complex. So I use I use genealogy or family trees to describe how all the people in a particular high technology worked together and stabbed each other in the back. There's a lot of that, and stole ideas from each other and so forth to actually create the modern technology. So I was kind of surprised by how wrong things were. So I try to straighten out the history of movie making, of sampling theorem, computers, computer graphics, of course. I also did a whole chapter on television, but MIT Press made me leave it out because the book was already 550 pages.
And so looking back, do you think, so you were at Xerox, then you were at New York University, where some of these technologies were invented or improved, nobody invents. Do you think back then people saw this coming, today's world coming? I mean, now everything is image, right? I mean, we are
right. I think nobody understood, and they couldn't understand the power of Moore's law. Moore's law was announced in 1965, and the way I put it in the book is that everything good about computers gets better by an order of magnitude every 5 years. Now, order of magnitude is a factor of 10, and that's basically all that we puny humans can think. If we can't think more than an order of magnitude. Basically, you have to change the conceptual values to leap to the next order of magnitude. But Moore's law says you're going to have one of these order of magnitude revolutions every 5 years, starting in 1965, when I made my first computer graphic, by the way. Right now, Moore's law factor, so the Moore's law factor was 1 in 1965. Today, it's sitting at 100 billion. Everything good about computers today is 100 billion times better than it was in 65. 11 orders of magnitude. No human being can possibly imagine what that is. Nobody could have predicted that. Nobody, including the engineers who built the chips. So people are always saying Moore's law is dead. I don't think so. The engineers who improved Moore's law, they're bound by the same order of magnitude block as the rest of us human beings. They have to get there to the current order of magnitude before they say, oh, now I can see how to push it, make those chips even denser. And in fact, just a couple of months ago, IBM announced a new 2 nanometer chip technology. I don't think Moore's law is dead. And I also think, we're going to hit 1 trillion in 2025. The Moore's law factor will be 1 trillion. What's that mean? Well, I just told you, we don't know. We just have to get there before we know what that means. Or another way to say it is, if you can think ahead of order of magnitudes, you can probably become a billionaire, because it's hard to do.
You're getting to my follow-up question that was about the future. So now that we still have progress in computer performance and storage and everything, but in the last few years, the only thing that has done for me is almost negative. I mean, I have higher resolution pictures on my smartphone, which I don't want, by the way. Sometimes I'm just taking a picture of some text. So what if computers become 1,000 times faster? What does it do in terms of graphics? I mean, we already have videos, we already have this image, and it's good enough for me.
Yeah, like I said, I don't think that you and I and Cindy can describe what it's going to be like 5 years from now. We just sort of have to get there to see what it feels like, and it's going to feel different from this. And this already feels different from 5 years ago, and definitely from 10 years ago. I mean, who knew about Zoom 10 years ago? The things I'm watching are AI. Let me just tell you a story about AI. First of all, I started in AI. Most people don't know this, in 1965 at Stanford. And I changed out of it because I didn't think it was going to happen in my lifetime. But now I'm thinking otherwise. Maybe it is going to happen in my lifetime, that we'll understand intelligence via the machine models. Alison Gopnik, my wife, and I we were on her sabbatical at Cambridge University 2 or 3 years ago, when one of my friends, John Bronskill, who was a pixel packer like myself, he wrote applications for Photoshop. So he approached me. He's working on his PhD at Cambridge. He said, Alvy, we don't have to program anymore. And I went, what do you mean? He said, well, read this paper. And he handed me a paper from a UC Berkeley AI department, the one that Allison works with. And it was a paper that I call the horses and zebras paper. The basic idea was, you take a GAN, a neural network of a certain kind, and you train it with 1,000 pictures, arbitrary pictures of horses, no text, just pictures. And you train it with 1,000 pictures of zebras, again, just arbitrary photographs, no text. And after it's been trained, you can submit a photograph, an arbitrary photograph of horses to the GAN, and it will return that same photograph, except every horse has been replaced with a zebra. And I looked at that and I said, wait, wait a minute, how does it do that? I don't think that's a well-posed problem. How does it do that? And John said, that's what I'm trying to tell you. We don't know. And it's too hard to reverse engineer to figure out what it does. It just does it. And all of a sudden, it started dawning on me, oh my gosh, here I always thought that I would understand intelligent machines when they arrived. And I'm thinking now, no, that's exactly what you can't do. They probably aren't intelligent if you can understand them. That, I'm not sure about that yet, but that's George Dyson's third law of AI, is that any machine that's simple enough to understand is not simple enough to be complex enough to be intelligent, and vice versa, something like that.
Right. Okay, we vastly exceeded the time we normally spend on a laser. Thank you very much for staying up till late. I know it's what was it, 10:30 in Canada, your time?
It's 10:38.
10:38. Okay, and thank you, Cindy, if you're still there. Thank you, the audience. Thank you for a very informative, very educational, very intense evening. And
yes.
Audience, if you go to lasertalks.com, you'll find links to this speaker's website a lot more information. Okay, thank you. Good night.
Okay, good night, everybody. Bye-bye.